Welcome back for another lecture. So we're going to keep talking about the Lewis structures. And in this slide, we see that on the left side, we have carbon that attached to 4 different elements, and they can be also identical. But the bottom line is carbon has 4 bonds. And in each bond, we have 2 electrons. So that means that carbon is octet. And just simply draw a circle around carbon and say, I see 4 electrons inside the circle, made 4 bonds, so it's octet. Okay. But if I did with the nitrogen, I see only 3 electrons there and made 3 bonds. And that means nitrogen is not octet. How can I make nitrogen octet? In this case, chemist has tendency to not show the lone pair, but if you see nitrogen attached to 3 atoms and there is no charge or whatever, and just simply add lone pair to nitrogen until you make it octet. Okay, so what do I see here? I see 5 electrons inside the circle and made 3 sigma bond. That's going to be 8. How about oxygen? Oxygen. So right now we see 2 electrons and made 2 sigma bonds. That's going to be 4. So we are missing 4 technically electrons to reach 8. So let's add 2 lone pairs to nitrogen. To oxygen, and that's going to be 6 electrons plus 2 bonds. That's going to be 8. And how about elements like, for example, chlorine, bromine, or fluorine, chlorine, bromine, iodine? And so example is this. Let's say we have an H attached to, for example, chlorine. Okay, is chlorine octet? Clearly, chlorine is not octet. And okay, so what we're going to do? Simply, we're going to add enough electrons to chlorine until we reach octet. Okay, and now I see 7 electrons. We made 1 bond, and that's going to be 8. Okay, and one that I want to actually kind of like be sensitive to it, and the first digit I'm writing. What's the first digit? The first digit is technically representing also the group of the element. Okay, chlorine is a group 7, so it's supposed to have like 7 electrons. Oxygen group 6, so we need to have 6 electrons around oxygen, and oxygen is going to be attached to 2 atoms, regardless of whatever, 2 atoms, and to make octet. How about nitrogen? Group 5. So how far I'm from 8? 3 bonds. 3 bonds. So I'm gonna, out of 5 electrons that I have as a nitrogen, I will share 3 of them with my neighbor. 3 of them with my neighbor to get to octet or 8. Okay. There's an example here. It says CHEM. Get the Lewis structure for it. So let's go after it. Okay. So the example that we have, it will be this. Okay. So we have CH2O, hydrogen group 1, carbon group 4, and oxygen group 6. Okay. So what we're going to say, you will say, I see 1 carbon, I see 2 hydrogens, and 1 oxygen. Of course, there is no charge, so no need to write the charge. And then say 1 multiply 4 electrons for carbon plus 2 multiply 1 electron for hydrogen, and 1 multiply 6 electrons for oxygen. That's going to give you 12 electrons. Okay. Never ever put hydrogen as a central atom. You don't have option. So in this case, hydrogen will go at. We have carbon and oxygen. We're going to sort them based on electronegativity. Oxygen has higher electronegativity than carbon. And again, reminder, ignore hydrogen. Okay, ignore hydrogen. Okay, so that means carbon is the central atom. Okay, carbon is the central atom, and we have 12 electrons. So let's go after the structure. Here is carbon, and we have 2 hydrogens. So I'm going to put the 2 hydrogens there, and I do have 1 oxygen. Totally, I have 12 electrons. What do I do with them? I'm going to build sigma bonds, and you need 3 sigma bonds. Okay, so I'm going to say I made 3 sigma bonds, and for each sigma bond, I use 2 electrons. Those are the 2 electrons I'm talking about. Okay, so now we are plus 6. What do we do them? We give them to the most electronegative element. In this case, it's oxygen, until we make it octet. Okay, so before I add the electron, I'm going to just simply draw a circle around each element. Okay. And I'm going to give oxygen 6 more electrons to make it octet. So minus 6. I use all the electrons. I'm done. Now, is oxygen octet? Yes, I see 7 electrons there, 1 bond, and that's going to be 8. So oxygen is octet. How about the formal charge for oxygen? Oxygen is a group 6. So supposed to have 6 electrons, but clearly it has 1 more. And now, how many electrons inside the circle do we see? We see 7 of them. So oxygen has minus 1 charge. Okay. So oxygen has minus 1 charge. It means oxygen got 1 extra electron. Okay. But what's the cost here? The cost, carbon is not octet. We can check carbon, hydrogen. Hydrogen is 1 plus 1, 2. Okay. How about the formal charge? Formal charge, hydrogen group 1. There is 1 electron around it. So it has 0 formal charge. Hydrogen is happy. How about carbon? Carbon, okay, so carbon, I see 3 electrons inside the circle and made 3 bonds. So carbon is not octet. Okay, carbon is not active. And I said, and under any condition, you have to make carbon active. Otherwise, it's not going to be stable. Okay, what's the solution for it? Solution for it, let's go after one of the lone pair from oxygen. I'm going to get rid of this lone pair. So that lone pair is gone. Now, what do I do with it? Okay, I will share it between carbon and oxygen. Okay, and now I need to redo the calculation here, whatever I wrote. I need to redo it. Okay, first bond is sigma, the second bond is pi. Okay, is oxygen active? I see 6 electrons. We made 2 bonds, so it's active. Okay, what's the formal charge? Oxygen is a group 6. I see 6 electrons around it, so the formal charge is 0. Okay, we didn't change anything about hydrogen, but how about carbon? Carbon, I see 4 electrons inside the circle. Okay, 4 electrons inside the circle, and forgive me, 4. And we made 4 bonds. Okay, we made 4 bonds, so I'm going to say 4. That will be 8. Carbon also is active. How about the formal charge? Carbon is a group 4. How many electrons inside the circle do you see? I see 4 of them. Okay, 4 electrons inside the circle, so I'm going to say minus 4. Okay, minus 4, and that's going to give me 0. Okay. Okay, so I got all the formal charges equal to 0, 0, 0 here, and of course this one also it will be 0. And we can prove it. Is it hydrogen? It has 1 electron, and minus 1, it will be 0. Okay, so all elements are either active or double. That means they have 2 electrons, like hydrogen, so they're fine. And also the formal charges all are 0. So that's going to be the best Lewis structure for such a molecule. Okay, okay, let's move on. The next subject. Okay, how do I calculate the formal charge? I already practiced some example, but again, I'm going to do it. And there's a formula for it. It says valence electrons minus non-bonding minus half of the bonding electrons. And okay, we can practice it, for example, for oxygen. And so formal charge for oxygen, if we use that formula, okay, oxygen is a group 6 minus, it says non-bonding. Those electrons are non-bonding. And these 2 are bonding. So I go minus 6 electrons, 6 non-bonding I see run, and I'm going to highlight them, 2 here, 2 there, and 2 there, 6 non-bonding, and then half of the bonding. How many bondings do we have? We have only 1 sigma bond, and we use 2 electrons for it. So 6 minus 7, okay, 6 minus 7, that's going to be minus 1. So that means the formal charge for oxygen, it will be minus 1. Okay, and if you repeat this one for hydrogen, it will be 0, carbon as well. Or use this method instead of using that formula, just simply draw a circle around each element, including oxygen. You can practice it with oxygen as well. And say this. Okay, element, I see hydrogen. Hydrogen is a group 1. How many electrons inside the circle? I see 1. So minus 1, that's going to be 0. How about carbon? Carbon is a group 4. How many electrons inside the circle do you see? You will say, I see 4 of them, and those are the 4. So it will be 0. Let's repeat this one for oxygen. Okay, for oxygen, oxygen is a group 6 minus how many electrons inside the circle do you see? I see 7 of them. So it will be minus 1. Again, where did I get the 7? Okay, I got it from the electrons that I see inside the circle. Okay, starting from here, 1, 2, 3, 4, 5, 6, 7 of them. Okay, I see 7 electrons there. And if you add all the formal charges, minus 1, okay, 0, this one also 0, 0, and so you get them equal to minus 1, which is the charge of CH3O minus 1. Okay, cool. Okay, so now we know how to draw Lewis structure of one compound until we get it acted. If we are supposed to have a charge, now we know how to calculate it, or then also how to pick the best Lewis structure. And I showed you, like inside the last during last lecture video. Okay, now I'm going to switch to orbitals, like what type of orbitals we have, how do we get those orbitals, what's the shape of them. Okay, the graph that you see in front, the cartoon that you see in front of you is showing you a bunch of s orbitals and also p. S orbital are spherical, while the p orbital, they have 2 dimples, and one is like they show with red, the second with blue. That means they have different sign. Okay, and then like if you ask a physical chemist or a chemist, they don't like to say, or treat electron as a particle. They usually treat it as a cloud, and they say, and then also they use electron density to refer to that cloud. So every time we are talking about electron, we will be using electron density. Electron density is talking about the chance of finding electron. The higher electron density, the higher chance to find electron there. Though that means that electron can be involved in chemical reaction. If you treat it with something, that electron might do something for you. Okay, the place that you accommodate the electron density in it, we call it orbital. Again, the place that we accommodate electron or the electron density, we call it orbital. you have 90% chance to find the electron. Why 90%? Because when you handle the Schrodinger equation, and this is the Schrodinger equation, we say Hamiltonian factor multiply an operator. This is just simply math function. Is really, really sophisticated, and it's going to give you energy plus psi. Okay, we get two answers every time we handle the Schrodinger equation. One of them is going to be energy, and the second answer you will get a volume. Okay, you get a volume, and what's that volume? That volume is technically showing you where your electron is. Okay, so you can say you will get an orbital, place that you can find the electron in it. Okay, as I mentioned before, the p orbital, it has two dimensions, and one of them is just like here red, the second blue or purple, any color that you see. It means like while you're moving from red to the blue one or purple, sign is changing. The best way to present it is going to be like this. So imagine you have a wave. So I'm going to say I have a wave. And here, our wave, for example, is positive, and then we go down there, it will turn to negative. Okay, so what do we have here? On X, we have phase. Okay, the phase up positive, down is negative. And what's this? That represents time, or also distant from technically, you can say, like later when we talk about electron, it will be distant from the nucleus, but here, let's just simply call it time. Okay, time. And the distance of the max point from the horizontal line, we call it amplitude, and we show it by A. Okay, amplitude, and we show it by A. Okay, whenever you hit this point, sign from positive is changing to negative. Okay, it's changing to negative. We call this point, we call it node. Okay, so what's a node? Is a place that sign of the wave will change from positive, will turn to negative. Again, this point here, minimum point to the horizontal line, you can call it, again, A or amplitude. Okay, these two are completely identical. So every time we pass that point, we're going to have a node. And again, what's the node? Place that you have zero chance, place that you have zero chance to find the electron. Okay, you have zero chance to find the electron, and usually we show it by this. Okay, we say psi2, probability of finding electron, psi2 is going to be equal to 0 inside node. Okay, probability of finding electron inside node, we show it here by psi2, and we say psi2 is going to be equal to 0. Okay, and one common node for any orbital, regardless of the nature of that orbital, it will be the nucleus. You have zero chance to find any electron inside the nucleus. And when we are talking about p orbital, we say p orbital, it has two lobes, positive and negative. Okay, and so we say positive, negative. And what's this? This is a node. Okay, this is a node, is a plane that is changing the phase from positive to negative. If your orbital is aligned with z, like we call it pz. If it's aligned with x, forgive me, or aligned with, say, y, if this one is x and that one is y, so I'm going to say this is px, and this one, it will be py. It doesn't matter really where you put x and y or p, but overall we have 3 p orbitals, and because we have 3 p orbitals, whenever we're talking about electron configuration, we show the p orbital by 3 boxes, and we can, when we say that p orbital is made of 3 boxes, the first one will be px, this is py, that is pz, and you can accommodate 1, 2, 3 electrons are pointing up, and then 3 they will be pointing down. So totally you can accommodate 6 electrons inside p orbital. Okay. How about the s orbital? S orbital is a spherical orbital. Always it will be spherical. Okay, so if this one is a s orbital, one s orbital, the 2s orbital is going to be a bit bigger, and that's going to be 3s orbital. So as we get far, when we get far from the nucleus, size of the orbital will be bigger. And those represent radius of the orbital. Okay, so size of the orbital gets bigger as we move far from the nucleus. Okay, so if I say size of orbital, size of 3s orbital bigger than the 2s orbital, and bigger than 1s orbital. How about the energy? Okay, energy. As you get far from the nucleus, energy of that orbital will go up, or energy of that electron sitting inside 3s orbital will go up. Okay, so I'm going to say energy of an electron in 3s orbital is going to be higher than an electron that's sitting in 2s, and that one sitting in 1s orbital. Okay. Next thing is going to be the attraction between two waves. What will happen if two waves reach each other, and we might get constructive or destructive interference. Okay, if two waves reach each other and they are in phase, okay, they are in phase. That means whenever the first one is up, the second one also is up. That means I'm going to get a constructive interference. Okay, let me show it this way. Okay, so imagine the first wave is up down, and the second wave also up down. Okay, when you add the first wave, I'm going to show it by side 1 to side 2, because they are in phase. This is the max point, and that one is the max point. They sit perfectly on top of each other. Okay, when you add them to each other, you will get a stronger wave. Okay, stronger wave than any original one. What does it mean? It means the amplitude of the new wave, if we call this one A, is going to be equal to, okay, let's call it A3, is going to be equal to A1 plus A2. A1 plus A2. This is constructive interference. In chemistry, we call it bonding. Okay, bonding interaction. Okay, bonding interaction. Okay, but what will happen if they are out of phases? Okay, if they are out of phases, they will cancel each other, and the amplitude of the new orbital, a new wave, it will be weaker. Okay, or maybe completely, you know, like disappear, and you will get zero amplitude. Okay, so the example for it will be this. Okay, so if this is the first wave, the second wave, it will be like this, down, up. Okay, call this one side 1, and that's side 2. They are opposite, and we call them out of phases. When you add them, the answer, it will be like this. This is going to be the answer. Technically, you will get really weak. Okay, you will get weak amplitude, or your wave, it will be maybe like that. It's a smaller one. Okay, so the new amplitude, A3, is going to be smaller than A1 plus A2. Okay, smaller than any of them. Okay, smaller than any of those two. And we call it anti-bonding interaction. Anti-bonding interaction. Okay, atomic orbitals, when they reach each other, they might reach each other in the right position. You might get bonding or anti-bonding interaction, and that's a good subject for another lecture. Thank you very much, and see you soon.